So we're going to talk about significant figures now. And like I said before, it's pretty difficult to find a math joke. Math humor is pretty far and few between. But here we go. We've got some digits here. And he's saying there, "Hi, I'm Tom. And this is Becky, my significant digit." Ha ha, get it? It's pretty bad, I know. But you got to do what you got to do. So we're talking about significant figures today and why certain numbers are significant in a value versus other numbers that are just holding a place that are not significant. So let's kind of dive in here, and hopefully this will explain to you a little bit about why when you punch numbers into your calculator and you're doing a calculation in math class or in science class, and your calculator spits out this humongous long number, and you're like, your first thought's probably, oh, it's wrong. And your second thought might be, okay, maybe it's right, but how much of it do I write down? Like, where do I chop this thing off? Do I round? What do I do? Here's the answer. There's actually very good reasons that we do what we do in science. Hopefully this will make all of your math make more sense too. So let's discuss here first the fact that there are two types of numbers in terms of our discussion here today. There are what we call exact numbers, and there are inexact numbers. Now, an exact number is like a dozen of eggs. There's exactly 12 eggs in a dozen. So if I'm counting something, I'm not going to have like 12.2 eggs in a carton. Because if you have 0.2 of an egg, you no longer have an egg, right? There's a lot of things like this where the number is a whole exact number. It's not inexact. Now, I don't want to split too many hairs here, but an inexact number could probably be a decimal as well. It's unlikely, but it's an exact unit of something. You can only have X amount of it, okay? Whereas an inexact number is typically something that's going to have a decimal in it. It may or it may not when you see it written on the page. But the point is that an inexact number is a measurement. It seems strange, but anytime we make a measurement, it's inexact. Like, there is some degree of inaccuracy. And when you report that number, you're essentially reporting how carefully you could measure something, to what degree of precision you could measure it to, based on the reported decimal that you put into that number. If you report too many zeros, or too few zeros, or too many decimal places, or too few decimal places, you are lying. And that's very important in science, and other scientists will nail you on it. So let's take a look here. I said, let's say you measure a piece of paper to be 220 millimeters. Okay, that's technically two significant figures. All right, the 2 and the 2 are significant. The 0 in that number is not significant. We'll see why here in just a second. You could also measure a piece of paper to be 216 millimeters. That contains 3 Sig Figs right there. Okay, there's 3 significant figures there, the 2, the 1, and the 6. The way that's reported, it's showing me that I physically measured out to 216. Okay, that last 6 is the number that I rounded to. Or you might say 215.6 millimeters. That's giving me 4 Sig Figs. That's saying I could measure out and guess that last tenths place. So there's obviously something going on here with zeros. And zeros are going to be the catch on all of this, because it's the way that we report that 0 and what we do with that decimal place that affects like what the total number of significant figures are. It affects how you're reporting and whether you're saying that you actually measured so far or you didn't measure so far. Maybe that person in the first instance there, where it's 220 millimeters, really was capable of measuring out to that 0 place, but they didn't report it correctly if they did. Okay, we'll see how that works out here in just a second. Let's look at measurements here. In any measurement, the number of Sig Figs that you show in that measurement is absolutely critical. So the number of Sig Figs is the number of digits that you believe to be correct by doing the measurement plus one estimated, or we could say guess digit, okay? In other words, in any measurement that you make, you get to estimate one number, one digit from that. And it's always the very last place in the decimals, okay? Or at the end of the number. It's the very last number that you write down. That's the one you get to estimate. Okay, so if we're looking at, for instance, a temperature scale here, which this was on a hike I took out in Texas, it was really hot that day, right? You can see from the scale there, it was a little bit over 100 degrees. That's hot. But look at this scale. If you look closely, it's almost a little hard to see here. If we look at, like, say, the 0 there, up to 10, let's see, there's 1, 2, 3, 4, 5 lines there. So we're jumping by 2s each time. So anytime you start to make a measurement, you have to understand how finely your scale is divided. And the scale on this thermometer here is not divided very finely. Like, I can't measure out to very many places. For instance, I could measure, say, since that goes by 2s, I could measure out to 2 degrees, right? That would be that first line up after the 0. Now, that's right on the line. I still get to guess one. Let's say it was just a little bit past the 2, okay? Then I would guess like 2.1, right? If it was right in the middle there, I might guess 3. Okay, but I get to guess one past that. Now, what if it's right on the line? What if it's right on that 2 line? Then I would guess 2.0, right? Get it? Because I still get to guess one number, and if it's smack dab on that 2, well, I know I'm on that 2 line, and I get to guess that it's 0.0 past the 2. So hopefully that makes some sense. Because think about it like this: could I guess 2.03? No, right? That is an absolute and utter lie. It's a failure of my reporting. There is no possible way I could measure out to 0.03 on that scale, because I'd be guessing 2 numbers. I get to guess 1, not 2. So let me tell you a short little story here. So a few years back, maybe like 2 years or so, I spent a summer working at Indiana University in their cyclotron. So that's their particle accelerator. That's where they do high energy nuclear physics. These are some real nerds here. This is like the real deal. If you've ever watched The Big Bang Theory, the folks that I worked with every day, they were essentially people like Sheldon. It was a very interesting place. I loved working there, but it was unique too. There's a lot of stories I could tell you about that place. But anyway, one thing kind of in my mind I remember. Well, first of all, I wasn't working on the particle accelerator, right? I got to see it, which was really cool, and talk to the folks that ran it. I was just doing some computer coding for them. So I'm sitting in this tiny little room with a bunch of other people that are typing away on computers, and it's very quiet, you know. And my boss had a graduate student in there, and the graduate student was working on his thesis, his final basically project for all of his culmination of his years and work there. And it was about neutrinos or something like that. And he was putting together his final presentation to present to this huge panel of physicists. So it had to be right and it had to be good because there's some really intelligent people that are going to be in here reviewing his work. And his advisor, my boss, was sitting in there with him on this day, and he was walking him through the presentation. He's going through the PowerPoint slides, and he gets to a slide, and I've got my back to them because I'm working on some code, and I hear my boss go, whoa, what's this number right here? And he goes, well, that's the value I got after I did my calculations. He said, how did you get that number? And he's like, well, that's what the calculator said. And he goes, there's no possible way you measured out 7 decimal places on that. And the kid that was there, I mean, he was he's working on his PhD. He looks at him and he goes, what do you mean? And his advisor was just like, you're basically lying, and all those physicists in that room are going to call you on it when you get there. They're going to look at you and be like, how in the world did you have a measurement device that could measure out that many decimal places? Nobody knows of one yet. Nobody's created one. And he had to basically walk him through what Sig Figs were, because the student had never heard of them. And I was honestly shocked, because I teach them every year in my astronomy class. So if you think this stuff doesn't matter, if you want to work in science or in engineering, believe me, it absolutely matters. Now, if you want to measure a house, If you're gonna like, pull out a tape measure and see how long a 2x4 is or something like that, you don't have to be that accurate. Nobody cares that you report out to X amount of decimal places, right? They're probably gonna laugh at you if you go to the lumber store and you say, I need something that's, 4.6332 feet. Right? That would be absolutely inane. There'd be no reason to do that. Um, so our measurement devices, when we're pulling things like tape measures, don't measure to that fine of a scale, so nobody really thinks about it, right? But when you're doing particle physics, when you're doing astronomy, better believe people are going to check that stuff. When you do science, people want to know that you're reporting your measurements correctly. Okay, so it's one thing if you make a measurement and you measure it, you know how to use your measuring device and report that correctly, but you can end up with some really weird numbers once you start adding, subtracting, multiplying, dividing. When you start doing math with the measurement numbers, the math is going to give you the full amount of digits that the calculation gives you. You're going to have to be the one that's smart enough to know where to chop that off at, where to round at. So I hope that makes some sense to you, and you don't find yourself in a weird position someday where your advisor looks at you and goes, "What's wrong with you, kid? You got no idea how to round a number? Do you have no idea how measurements work?" Right? And this is how it really works. So when you're doing math in math class and you get an answer, you don't have to raise your hand and go, "Hey, Mrs. So-and-so, what do I give you here? I've got all these digits." Well, how many digits you want, right? And your math teacher will usually go, "Give me one after the decimal place, give me tenths." Because they don't want to grade all those extra numbers or look very carefully at it, which is understandable. They just want to see that you can do the math, right? Now, if you start doing this in math class, some of your rounding can give you some funny numbers if you're doing it appropriately, and your math teacher might count it wrong. So you better check with your math teacher with how they're grading things, because a lot of the time they're probably not checking Sig Figs. But if you're doing it right, sometimes your reported results can actually look kind of funny, right? So let's take a look here at some example measurements. Here is a beaker, a graduated cylinder, and a burette. So the beaker at the top there, when you look at that, okay, you get to make a measurement, and remember, you get to guess one number. So first of all, understand the scale, okay? It's going 20, the next line is 30, the next line is 40, right? The next line is 50. Well, it's not quite to the 50, and it's definitely after the 40. So we can, without a doubt, say that it's at least 40. But I don't want to round to 40 because we know that it's further than that. And looking at that line, I'm going to guess that maybe it's just a little bit past halfway, right? You can always divide those lines, the measurements, in half. So you kind of guessed based on, is it halfway? Is it a little more than halfway? A little less than halfway? So we know it goes 40, 50. So I'm going to guess maybe, 47 milliliters, because it's just a little past 45 milliliters. Could you have guessed 46? Absolutely. Could you have guessed 48? Absolutely. 49? Sure. Because that last digit is a guess. The 6, the 7, the 8, the 9 is a guess. Now, 45 would probably be clearly wrong, right? So 49 would maybe be a little bit iffy. You're probably not doing a good job of your measuring. But, that last digit is a guess. And when you report that, you're reporting that you guessed out to that 7, okay? Could you say 47.1? No, because that's a lie and it's stupid, right? There's no way you could measure or even guess to 0.1. You just can't divide it that carefully. Your scale doesn't go that far. Let's do the graduated cylinder. So, before I go on, how many sig figs is in 47? There's 2 digits. There's no zeros. It's easy. There's 2, okay? So how do we do that? Well, I just said here, the 4 we know for sure, plus the 7 that we had to estimate. That's 2 digits. So you get 1 estimated digit in every number, every measurement that you make. Here's the graduated cylinder. Let's look at the graduated cylinder. First of all, check the scale, first step, right? It goes from 35, the big number at the top there is 40. So 35, 36, 37, 38, 39, 40. They're going by 1 each time. Okay, so if you remember how to measure in a graduated cylinder, you measure to the bottom of the meniscus. So looking at that, I can see that I'm between 36, the big line's 35, 36 the next little line, and 37, which is the line after that. So I know I'm at 36 for sure, okay, but I get to guess a little bit, right? So I'm part way to 37. Am I halfway? You might guess 36.5. To me, it looks like it's just maybe a smidge over that. So I guessed 36.6. Hopefully you can see how that, you're certain to 36, right? Because it's past the 36 line, and then you're going to get to guess that last little decimal. Since we divide the lines into little tenths, we can guess 0.6. You could guess 0.5, right? So both of those would be very correct answers. How many sig figs is that? 3, right? It's 3 sig figs because there are 3 digits there, and there's no zeros involved, so that's very helpful. But the 36 we knew for sure, plus the 6 that we had to make our estimate on. Okay. Now the Buret. This one's a little different. This one you actually measure downwards, so it reads from the top down. You still measure to the bottom of the meniscus, but the scale goes from the top down. So you know how the 20's at the top, 21's at the bottom? So let's look again. We've got 20, and then it makes this big jump to 21. So 20.5 is right there in the middle at the next big line down. So this is a very fine scale here. So if we start going, let's look here. It would go 20, 20.1, 0.2, 0.3, 0.4, 0.5. Okay, so that's what the lines are divided into 0.5, those little lines. So when I make my guess, I'm going to look at that and I'm going to go 20, 0.1, 0.2, 0.3, right? I'm certain to 0.3, but it's past 0.3. I'm measuring from the top down. So I'm going to get to guess that last number, and I'm going to guess 20.38. But you could have guessed 20.39, 20.37, 20.35 would probably be pretty off, right? It's definitely not halfway between those two lines, right? How many sig figs do we have there? 4. Do you see how I was able to measure out to an additional decimal place because the scale of my measurement device was better? This is why reporting like this is important, because depending on the measurement tool that the physicist or the scientist uses, it will go to a certain amount of decimal places, and then you get to guess, estimate that last one like we just did, the 8, right? So if 2 different scientists use 2 different scales and make 2 different measurements, they may not be as fine of a measurement depending. So they need to report that appropriately so that each person knows like how far they could be off. Because when you're talking about these ridiculously large or ridiculously small numbers, you know, a decimal place can mean the world to whether the world ends in the universe ends in the big crunch, or the universe expands forever and ever and ever. Like there's big differences into how that plays out in physics. So in this one, we have 20.3, which we know for sure, plus an 8, which we had to estimate. So there are technically here, oops, oh, went through too fast, sorry. Let me pop that through. I didn't put that down there. There we go. So there are 4 sig figs there, right? That's why there's 4 sig figs there. Now let's talk the rules for 0, because those zeros can be confusing. You can see here that 0 is significant because it's part of the number that we knew for sure. But sometimes it's not part of the number that we knew for sure. It's just holding a place. So how do you tell? Here's the rules, and you might write these down just so you can remember them. Leading zeros are never significant. Okay? Embedded zeros are always significant. So if they fall between digits, they're always significant. Trailing zeros are significant, but only if there's a decimal point. So there has to be a decimal point in the number for the zeros that are after it to be significant. Okay, so one way to figure this out would be to change your number to scientific notation, because the number in scientific notation is always the sig figs. You report all of the sig figs in your numeral value in scientific notation. So let's do some examples here, and we'll see if we can figure out the number of sig figs and what the scientific notation would be. So here's the first example. We've got 0.00682. Pause it for a second and see if you can figure the number of sig figs. I'm going to keep rolling through this, so pause it each time for yourself and see if you can guess the right number, okay? So here we go. Sig figs in this number. There are 3. Okay, why are there 3? There's 3, which are 6, 8, and 2, because all those zeros before that number are not significant. Now I know there's a decimal place in there, but the decimal is before there's actually any actual numbers that are significant. So anytime you have zeros, even if there's a decimal out there, they're just holding a place if they're in front of the number. Okay, there's 3 sig figs. In scientific notation, remember I get to keep one number outside the decimal, so I need to move the decimal 1, 2, 3 over, and I've got 6.82. I keep every significant figure in my scientific notation, but only one number goes before the decimal. So I would specify that as 10 times 10 to the negative 3, because I moved the decimal place 3 places. Pretty easy, right? Okay, here's another one. 1.072. How many sig figs are in 1.072? Every single one is significant. The 0 is significant because it comes between 2 other numbers. Okay, you really did measure out to 1.072. Okay, there's 4 sig figs there. Now when I do this in scientific notation, it's going to look a little strange. We wouldn't normally do this. It's the same number. All those digits are significant. You've already got only one number in front of the decimal, so you don't have to move it. So it'd be like times 10 to the 0, which we would never really do, but I just did it so you could see. The next one, 300. Okay, ask yourself the rules here. The zeros come after a digit there, which is significant. Is there any decimal point specified? There is not a decimal point specified. So those zeros are just holding a place. There's only one sig fig, which if we put that into scientific notation, we whack off those zeros, and we have 3 times 10 to the 2, right? So when I would convert that back out, I'd have 300, right? So those zeros are not significant there. I don't know what the measuring device was. Did the measuring device go by hundreds, or did it actually go by ones? If it went by ones, then maybe I did measure out 300 exactly, like right on the money. But if I'm reporting it like that with no decimal in it, I'm saying that my measurement device only measured by hundreds. So I had to guess that, okay? So there is a way to do that. There's a way to report it and show that you physically did measure out to 300 precisely. And this is how you do it. And it'll look strange, but if you put a decimal after that number with those zeros in it, you are literally saying that every single one of those digits is significant. So it's 300 decimal point, right? If there's a decimal after that number somewhere, all of the zeros are significant in it. Okay? So if I put this into scientific notation, I need to show that those zeros are significant so that other physicists doing calculations can understand it. And the way to do that is to count them as significant numbers. 3.00 times 10 to the 2. Totally legit. Hopefully you can see the difference between the two of these. So in one I'm specifying I really did measure out to that 0 on the 300. And the other one, I'm saying that I had to just round it and guess it to that 3. Right? So my measurement scale was very different. My device had to have been different. What if I had this? Same thing, right? There's 4 sig figs. So my corresponding scientific notation needs to be 3.000 times 10 to the 3. Hopefully some of that makes some sense. I would write down these examples just so you have them to look at, because if you've got an example worth 1,000 words, right? You can just glance at it and go, oh, which of these does my thing match? Okay, so those are what the rules are for zeros. Other than zeros, everything else, if it's a digit, it's significant.
I wanted to give you a quick little demonstration here of why leading zeros are never significant. It's a hard concept for folks to grasp sometimes, so I wanted you to see a visual. It basically just comes down to the fact that they're holding places, and when we convert from units, we need to just move that decimal different directions, and we don't want to have suddenly a reporting of more significant figures than there really are. So that's why leading zeros are not significant. So what I've created here is a decimeter ruler. Why anybody would ever use a decimeter ruler is beyond me, because it's not a very fine-grained scale, is it? So 1 decimeter is 10 centimeters. So there's a decimeter, there's a decimeter. So we go 1, 2. I can measure in decimeters, and I'm going to put it out to a decimal in decimeters. So let's say I've got a measurement, and I'm going to zoom in a little bit more here so you can see. Down there we go. Okay, so it's less than 1 decimeter, and so these right here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are tenths of a decimeter. Okay, and let's say I'm going to make a measurement, and I'm measuring something that is literally only that long. It's from there to there. Now, why you'd use a decimeter ruler to try and measure something that's that small, I don't know. But let's just say you did. That's all you had. So you measured something that was to about right there. Okay. So if this right here, this line right here is 0.1 of a decimeter, okay, this line right here is going to be 0.05 decimeters. So I just measured something that's 0.05 decimeters. Okay. Now, if I need to use that in an equation somewhere else, I need to do some math with it. I need to know how many sig figs there are. Well, you already know that leading zeros are not significant, so there's 1 sig fig. Oops. Oop. 1 sig fig. Okay. Now, let's say I'm using that somewhere where I need to add or subtract or something like that, and I need to convert it into centimeters because I need to have the same units, so, or maybe millimeters. Millimeters would be a better example. So to convert this into millimeters, I would need to move the decimal place 2 to the right to get it into millimeters. So converting it into millimeters, I would have 5 millimeters, okay, which is of course also 1 sig fig. The reason I could not report that to 5.0 sig fig, 5.0, like if I said that 0 was significant, I'd have to have 2 digits in my other conversion here. 5.0 is showing 2 sig figs. That's wrong. I can't have 2 sig figs in that. Let's look at it over here on an actual meter bar. If I'm looking at it on a meter bar, right, that's a decimeter. Okay, if I go down here to the millimeters, each little line is a millimeter, and if I'm reporting out to 0.05 decimeters, that's right there. Okay, that's 5 millimeters. That's 5 of those little lines. Could I have ever measured to 5.0 on that scale? Oh, heck no. Like, I got to guess that one number. Now on this scale, I could measure to 5.0, like, because I could measure. I've got this divided into millimeters. But if I didn't have my other scale that I was measuring with divided into millimeters, okay, then if I make that guess, 0.05 decimeters, when I convert it and move the decimal over, that 0 is just holding a place, right? It's not significant. So that keeps it proper for me when I move things the right direction. Okay. Conversely, if I'm moving something the other direction and I end up with a bunch of zeros at the end of my number, they're also just holding a place unless I have a decimal in there, right? If I went the other direction. So hopefully that made a little bit more sense. Let's just go ahead and go the other direction with that, just so you can see it here. So let's say that I measure something with a meter bar. Say, I'm going to get rid of the units there so it doesn't confuse you. And I measure this, and what I measure happens to be one of these sticks long plus a little bit. But my units are in whole meters, so I measure it and I round it and I say it's 1 meter, okay? So if I measure it to 1 meter and I get 1 meter as my measurement, if I wanted to convert that into millimeters, right? I need to move that decimal a lot. So my decimal's there. I'm going to have, that's going to equal 1,000 millimeters. Okay. With my units, no way did I measure to that kind of precision, right? I didn't measure to that precision. So I still get to keep one sig fig. So, and that is showing one sig fig. That's why I wouldn't want to report this as 1000 decimal millimeters, because now I'm saying I had 4 sig figs in there. That is definitely not right. See that? So, if you're even going the other direction, it makes no difference. Those zeros are just holding a place because I'm converting between units. Okay, it's only what matters is how many units I physically measured and the 1 unit that I guessed in the original measurement scale. Like all the converting, we don't want to count those as significant. That's why we've got these funky rules for the zero.
All right, let's dive into the rules specifically for addition and subtraction. Okay. In addition and subtraction, there's different rules than there are for multiplication and division. Now, in addition and subtraction, the last digit that you keep is set by the first doubtful digit. So, let's work through this problem and then I'll try to explain it a little bit more. Okay, looking at the problem there, you've got to round that problem to 8.04 because your answer can only contain one doubtful number. Okay, we've underlined the doubtful digits here. Okay. So by doubtful, I mean the digit that they estimated when they made their measurement. So these are 3 measurement numbers here. I've measured 4.7832, 1.234, 2.02. So each person that made those measurements guessed out to that last number. So I only get to keep the number up to the least precise guess that was made in all 3 of those numbers, which happens to be out to that 2. So I would get to keep, after I add all those up, 8.03, but the 3 is going to round up to a 4 because it's 5, because 7 is 5 or more. Okay, so you do round, and there's different ways of doing this rounding, and depending who you work for or what you do in life, you'll be given specific ways you have to do it. This is the way that I do it, and I think it's a pretty simple way. If it's 5 or more, you round up. Okay, otherwise you just chop them off. Let's look at the example below that. You've got 2 numbers you're subtracting, no different. Line up your decimal places. The first step in addition and subtraction, write it down and line up the decimal places. After that, you just go out to the end of the number and you're going to chop off like wherever the shortest number is. Okay, so in this case, the 1.0236, 6 is the shortest length of digits there once we've lined the decimals up. Okay, so we're going to round to that 9 there in our answer, which essentially means dropping the 2. Okay, and I've got my answer proper. Okay, so let's look at multiplication and division. I guess before I do that, let me explain this. The reason that there's a different rule for addition and subtraction versus multiplication and division is, think of it like this. When you're adding and subtracting numbers, your units are always the same, right? I can't think of any math where you're going to add and subtract numbers with different units. Like if you're trying to say, if it's, 3 miles to the store and I've gone 4 miles, how many miles, so that doesn't work. if it's 8 miles to the store, right, and I've gone 4 miles, how many miles do I have left to go? You would subtract to get 4 miles, right? In every part of that question, the units are miles, okay? The reason that we can do this is because we're comparing apples to apples, okay? We're comparing the same things when we're doing the math. So what we want to do is the measurement that's been made with the least amount of precision, we only want to report out to that precision when we report, because otherwise we're saying that we were able to measure to a better value, to a better precision than what the measuring devices were actually capable of. And that really does matter. So in multiplication and division, the rules are a little bit more confounding. The rule's simple, but the reason for it's a little different. So we have to have a different rule for multiplication and division because oftentimes you're comparing two numbers, you're calculating two numbers that have different units, right? If we're trying to figure out like meters per second, right? Meters and seconds are two very different units, right? If we're comparing miles per hour in terms of how fast you're going, right? Your speed. Well, you're comparing miles, which would be using one type of a measurement scale, all right, and hours, which is a time measurement scale. So we're comparing time and distance. So those two scales, there's no way to have the same type of measurement precision, if you will. Like they're each their own thing. So basically what we do is we kind of like do the best that we can with it, and we just round to the total of the smallest amount of significant figures of any of the numbers that we have. So anytime you have division, multiplication going on, you're just going to keep the smallest amount of sig figs that you have in either number that you start with. So the answer contains no more sig figs than the least accurately known number that you started with. So there's no lining up the decimal places. There's no going out as far as you can go to the shortest number of decimal places. Here, all we're going to do is do the math and then round it to whatever the smallest amount of decimal, or the smallest sig figs that we had in the starting numbers. So look at this first question here. 2.8723 times 1.6. Well, let's look at those two numbers we're starting with. 2.8723 has 1, 2, 3, 4, 5 sig figs. 1.6 has 2 sig figs. So my answer is going to have 2 sig figs when I'm done. Don't worry about where the decimal is. Total, complete total for the answer can only be 2. And sometimes that means like some really weird looking stuff. It's okay. So the answer is 4.59568. We're going to round that to 4.6 because the 9 rounds the 5 up to 6. And your answer is 2 sig figs. Looks totally nice, doesn't it? Let's look at the division one below. 4.52, 6.3578. 445.2 has only 3 sig figs. So we're going to round our answer to 3 sig figs. Our answer comes out to 7.1093775. If you reported all that, you're reporting a bunch of lies. You're a big fat liar. So what you need to do is round that to 7.11. And now our answer has 3 sig figs. See that? Pretty slick, huh? So that the rules are different. Let's give it a little quiz here. Let's give it a try. Take your time on this. Go slow. So I'm going to go through it fast. Pause the video where you need to. Okay, let's give the sig figs for these numbers. 4500, how many sig figs? There are 2 sig figs there, the 4 and the 5. 4500 decimal. How many sig figs? There are 4 sig figs. The zeros are significant because that decimal's in there. How about 0.0032? Be careful here. There's a decimal, but all those zeros come before the number, which means there's only 2 sig figs there. Now I've got both situations. I've got zeros before the number, I've got a decimal, and I've got zeros after the number. What to do? You might want to write down this example. There are 4 sig figs here. The zeros in front don't count. The 0 at the end does, because there's a decimal in there, and it comes after other digits. So 4, 0, 5, and 0 are all significant. Okay, so now what I'd like you to do is to try this math out. Punch these numbers in your calculator and see if you can give the numbers to the correct sig figs. Okay, see if you can give the numbers to the correct sig figs. So first one here is an addition problem. So remember what you're going to do with the addition. Okay, what you're going to do there. And our answer, pause it first here so that you can figure it out. Here's the answer. Okay, so your answer if we look at these things here, if we were to line them up, okay, 5088 is what our answer is going to be. 0 in the 550 is the first doubtful digit. So we're going to have to round to, we're not going to have any decimal places after that number. Okay, it doesn't matter what's out in front of it because we've lined those decimals up. Okay, so line them up. Let's do the subtraction problem below here. Okay, see if you can figure that out. Pause it if you need to here before I give you the answer. Here's the answer. The answer is going to be 0.03. Okay, the 4 in the 1.34 is the first doubtful digit, right? Because 0.367 extends out further than the 0.34. So we're going to have to chop everything off, our answer off, right there at the 0.03. I get to have 2 places after the decimal because 1.34 only has 2 places after the decimal. Those are the rules for addition and subtraction. Next, let's do some multiplication division. So these two, you don't have to type in the parentheses there. I just did that so you could set them apart, like just how you multiply 2 numbers together. I don't want you to be confused by the scientific notation multiplication signs. So in your calculator, you don't have to necessarily type in parentheses when you do these. So remember how to type in scientific notation. Don't use that times key until you're ready to multiply. The times 10 to the 3 times 10 to the 4 is the EE key, or the EXP key, or the times 10 to the X key. So it's the scientific notation key, the exponential key, not the multiplication, and don't type in that 10, okay? So see if you can get this. Here's the answer to the first one here, okay? Oops, sorry, I had a little thing there for 0.34. That's important. Okay, here's the answer. 7.4 times 10 to the 7. All right, I kept it in scientific notation. I get to keep 2 sig figs. Why do I get to keep 2? Because 1.3 is the smallest number of sig figs that I have up there. Okay, 1.3 is less sig figs than 5.724. I'm not keeping out to 0.4 because there's 1 decimal after 1.3. I'm keeping out to 0.4 because 1.3 is 2 sig figs. Right? This is the only time I count them, really, is in multiplication and division. Let's try another one, okay? We're going to divide here, and here's the answer, so pause it if you need to. 6.3 times 10 to the 5. I get 2 sig figs. Okay, boy, look at this. This one hopefully made it come home clear here, right? In multiplication and division, I have to count total sig figs. So 6305 has 1, 2, 3, 4 sig figs, right? How many sig figs in 0.010? If you said 2, you're right. Those 2 are significant. The other zeros that are just holding a place. Okay, so we get to report out to 6.3. And I gave you an example here of the subtraction situation here. If I subtracted those numbers there on that second math problem there, see how I line up the decimal places? And then I can just go out to the shortest amount when I do my answer. So I know it's a pain in the butt to write out longhand what addition and subtraction, because you just type in your calculator. But if you write it out longhand and line it up like you would in old school math before we had calculators, you can really clearly see how far you should report, right? 0.03. You round up that too. So hopefully that made some sense, and you now understand kind of why we do this. We're going to have a quiz over this. You're gonna have to use all these things, significant figures, scientific notation. But all in all, throughout the course, I'm not gonna kill your grade for reporting incorrectly to sig figs and things like that. This lesson's kind of a standalone because I want you to understand why we do it. And when I report my answers, if you're like, my answer doesn't match, it's probably because you didn't use sig figs or you didn't put it in scientific notation. So hopefully this will help you out in your future life and understanding how science works. That's it for today.